Welcome to this coding problem walkthrough. In this video, we'll be solving an interesting problem from LeetCode, problem number 237, delete node in a linked list. This problem is a classic interview question that tests your understanding of linked list manipulations. Let's dive in. In this problem, you are tasked with deleting a specific node from a singly linked list, but there's a unique twist. Instead of having access to the head of the list, you're only given a reference to the node that needs to be deleted. This makes the problem different from standard linked list deletion problems where you typically have access to the entire list. Your solution must directly modify the linked list in place without creating a new list or using any additional memory. One important constraint here is that the node to be deleted will always be a non-tail node, meaning it will never be the last node in the list. The goal is to return the modified linked list with the given node removed while ensuring the rest of the list remains valid and in its original order. Let's look at some examples to understand the problem better. In the first example, we're given a linked list with nodes 4, 5, 1, 9, and asked to delete the node with value 5. To achieve this, we copy the value from the next node, which is 1, into the current node. Then, we adjust the next pointer of the current node to skip over the next node, effectively removing it. The resulting list becomes 4, 1, 9. Similarly, in the second example, the input list is 4, 5, 1, 9, and the node to be deleted is 1. By copying the value 9 from the next node and updating the pointers, the list is modified to 4, 5, 9. This approach avoids directly deleting the current node and instead removes the node indirectly by overwriting it. In the third example, the linked list is 1, 2, 3, 4, and the node to be deleted is 3. Following the same approach, we copy the value 4 from the next node into the current node, and then update the next pointer of the current node to skip the node with value 4. The linked list is updated to 1, 2, 4. Now, let's consider the problem constraints. The linked list can have between 2 and 10,000 nodes, and each node's value is between 1 and 1,000. Additionally, the node to be deleted is guaranteed to be valid and is never the tail node. This ensures that our solution will always have a next node to work with, making the problem more manageable. There are a few edge cases to keep in mind while solving this problem. First, if the linked list has exactly 2 nodes and you delete one of them, the list will be left with just a single node. Second, the node to be deleted might have a unique value, meaning its value doesn't appear anywhere else in the list. For example, deleting the node with value 5 from 4, 5, 1, 9. Lastly, the node to be deleted might have a value that appears multiple times in the list, such as deleting the first occurrence of 5 in 4, 5, 5, 9. It's also important to note that you're required to modify the list in place without using extra memory. To achieve this, you'll copy the value of the next node into the current node and then update the next pointer to skip over the next node. This effectively removes the next node, accomplishing the task of deleting the current node. When approaching this problem, the standard brute force method for deleting a node in a singly linked list involves starting from the head, locating the node just before the target, and updating its pointer to skip over the target node. However, in this specific problem, we are not given access to the head of the linked list. This makes the brute force approach inapplicable because we cannot traverse the list to find the node preceding the one we want to delete. Instead, we turn to a more optimized solution using pointer manipulation. The intuition here is that, rather than directly deleting the target node, we can copy the value from the next node into the current node and then update the current node's pointer to skip over the next node. This effectively replaces the target node with the next node and removes the next node from the list. While there are alternative approaches, such as using recursion or simulating a dummy head, these methods are either unnecessarily complex or violate the problem's constraints. For this reason, the pointer manipulation approach is both the simplest and most efficient solution. Now, let's understand why the pointer manipulation approach is particularly well suited for this problem. First, the constraints explicitly state that we only have access to the node to be deleted, not the head of the list. Second, we are guaranteed that the target node is not the tail, which means it will always have a next node. These conditions allow us to use the next node's data and pointer to effectively overwrite the target node, eliminating the need for head access. This approach is efficient, with a time complexity of 1, as it only requires a constant number of operations. Additionally, it avoids the need for extra memory, giving it a space complexity of 1. However, one trade-off is that this method does not free the original memory location of the node. While this could be a concern in languages like C or C++ where manual memory management is required, it's not an issue in managed languages like Python or Java. Alternatives like brute force and recursive methods fail due to the lack of head access, and using a dummy head is unnecessarily complex given the problem constraints. Therefore, pointer manipulation emerges as the clear choice. The final algorithm involves 3 simple steps: copying the value of the next node into the current node, updating the current node's pointer to skip the next node, and effectively removing the next node from the list. Finally, let's analyze the efficiency and summarize the solution. From a complexity standpoint, the time complexity is 1, because the algorithm performs a fixed number of operations regardless of the size of the list. The space complexity is also 1, since no additional data structures are used. In conclusion, the pointer manipulation approach is the most efficient and straightforward technique for solving this problem. It aligns perfectly with the given constraints and avoids unnecessary complexity. This solution demonstrates the importance of thinking creatively and adapting standard techniques when problem constraints prevent traditional methods from working. The problem asks us to delete a specific node in a singly linked list, but with an important limitation: we are not given access to the head of the list. Instead, we are directly provided the node to delete. For example, if the list is 1-2-3-4-5 and we are asked to delete the node with value 4, the resulting list should be 1-2-3-5. This means we need to modify the structure of the list starting from the given node itself. A few constraints are critical here. The linked list is singly linked, meaning each node only points to the next node, and the input node is guaranteed to be neither null nor the tail node. This ensures that the next node always exists, which is essential for our approach to work. Since we don't have access to the head of the list, we cannot traverse it to find the previous node for traditional deletion. Instead, we directly manipulate the given node to mimic the deletion by focusing on its value and pointer. The first step is to verify the input, ensuring the node is valid and not the tail. Next, we overwrite the value of the current node with the value of the next node. For example, if the node to delete has the value 4 and its next node has the value 5, we replace the value 4 with 5. Once that's done, we bypass the next node by updating the current node's next pointer to skip over it. Specifically, we set n.next to n.next.next, effectively removing the next node from the list. This manipulation creates the illusion that the given node has been deleted. To further refine the process, let's address edge cases and clarify the result. The algorithm relies on the guarantee that the input node is not the tail, as accessing n.next for a tail node would lead to invalid operations. Assuming valid input, the node is effectively removed without disrupting the structure of the list. For instance, consider the list 1-2-3-4-5 with 4 as the node to delete. First, we copy the value 5 from the next node into the current node, temporarily making the list look like 1-2-3-5-5. Then, we update the next pointer of the current node to skip the next node, resulting in the final list 1-2-3-5. This approach achieves the desired deletion without needing access to the head or prior nodes. The output of this process is a modified linked list where the specified node has been removed, resulting in 1-2-3-5 for our example. This works because we have effectively replaced the target node's value and bypassed its reference in the list. By overwriting the value and skipping the next node, we achieve the deletion without requiring access to the head. The skipped node is no longer referenced and will eventually be cleared from memory by garbage collection in languages like Python or Java. However, this approach has limitations. It cannot handle cases where the node to delete is the tail, as there is no next node to copy from. On the positive side, the algorithm is extremely efficient, running in constant time and requiring no extra space, making it well suited for this specific problem. When considering edge cases, it's important to confirm that the input node is not null, as the algorithm cannot proceed without a valid node. Similarly, the algorithm cannot delete the tail node since it relies on copying the value of the next node, which does not exist for the tail. In terms of complexity, the algorithm is highly efficient. The time complexity is 1, because all operations, copying a value and updating a pointer, are performed in constant time. The space complexity is also 1, as no additional memory is allocated. This makes the solution both time and space efficient, but it is tailored specifically for the constraints of this problem and does not generalize to all deletion scenarios in a linked list. This problem requires us to delete a node in a singly linked list without access to the head of the list. Instead of directly removing the node, which is not possible without head access, the key idea here is to mimic the deletion by copying the value of the next node into the current node and then bypassing the next node. Explanation. 1. The list node class defines the structure of a singly linked list node. Each node has a val, its value, and a next pointer to the next node. 2. In the delete node function, the parameter node is the node to be deleted. Importantly, we do not have access to the head of the list, so we must modify the list directly starting from this node. Step 1 * copy the value of the next node, node.next.val, into the current node, node.val. This effectively overwrites the current node's value with the next node's value. For example, if the current node's value is 4 and the next node's value is 5, after this step, the current node will also have the value 5. Step 2 * update the next pointer of the current node to skip the next node, node.next equals node.next.next. This removes the reference to the next node, effectively deleting it from the linked list. Continuing the example, if the list was 3-4-5-6, it will now become 3-5-6 after removing 4. Key points. The solution works in 1 time complexity because it only involves a constant number of operations, copying a value and updating a pointer. This approach modifies the list in place without requiring additional memory. It's important to note that this method cannot delete the last node in the list because there is no next node to copy from. This concise implementation effectively solves the problem while adhering to the constraints of the question. This is the Java implementation of LeetCode problem number 237, delete node in a linked list. The logic mirrors the provided Python equivalent. The key steps involve copying the value of the next node into the current node and then updating the next pointer to skip the following node. Key differences in Java include explicit type declarations, the use of a class-based structure for list node, and the lack of built-in reference semantics as in Python. This implementation is concise and efficient, operating in 1 time. Here, we're tasked with deleting a node from the middle of a linked list. The input linked list is 4-5-1-9, and the node to delete is the one with the value 5. First, we copy the value of the next node, which is 1, into the current node. This means the value 5 is replaced with 1, and the linked list now looks like 4-1-1-9. Next, we update the current node's next pointer to skip over the next node entirely. By doing this, the second occurrence of the value 1 is removed, resulting in the updated linked list, 4-1-9. The node with the value 5 has now been effectively deleted from the linked list, and we've achieved this without needing access to the head of the list. The final linked list is 4-1-9. Now, let's look at another example. In this case, the input linked list is 1-2-3-4, and the node to delete is 3. To begin, we copy the value of the next node, which is 4, into the current node. This means the value 3 is replaced with 4, and the linked list now appears as 1-2-4-4. Next, we update the current node's next pointer to skip over the next node. This effectively removes the second occurrence of the value 4 from the list. As a result, the updated linked list is now 1-2-4. At this point, the node with the value 3 has been successfully deleted. The final linked list is 1-2-4. Let's move on to a shorter linked list example, where the input is 10-20-30, and the node to delete is 20. First, we copy the value of the next node, which is 30, into the current node. This updates the value 20 to 30, so the linked list becomes 10-30-30. Following the same process, we now update the next pointer of the current node to skip over the next node. This action removes the second occurrence of the value 30 from the list. As a result, the linked list is updated to 10-30. At this stage, the node with the value 20 has been successfully deleted. The final linked list for this example is 10-30. To summarize, the algorithm for deleting a node in a linked list works by copying the value of the next node into the current node and then adjusting the next pointer of the current node to skip the next node entirely. This approach makes it possible to delete the node without needing access to the head of the linked list. By overwriting the input node's value and updating its pointer, the node is effectively removed from the list. This efficient method is especially useful when the head of the linked list is not accessible. The time complexity for this problem is O1, which is constant time. This is because we are given direct access to the node that needs to be deleted. There's no need to traverse the linked list to locate it. Let's break down the operations. First, we copy the value of the next node into the current node using the statement node.val equals node.next.val. This is a simple assignment operation, which takes constant time, or O1. Next, we update the next pointer of the current node to skip over the next node by setting node.next equals node.next.next. Again, this is another constant time operation. Since these two operations are performed sequentially, the overall time complexity is O1 plus O1, which simplifies to O1. Importantly, this efficiency is independent of the size of the linked list because we are only working with the given node and its immediate neighbor. Now, let's discuss the space complexity. The space complexity of this solution is O1, or constant space. This means that the algorithm does not require any additional memory allocation or creation of new data structures. All the operations are performed in place directly on the provided node and its pointers, using only the memory that is already part of the input. As a result, no extra space is used. Additionally, the time and space complexities remain consistent regardless of where the node to be deleted is located in the list, whether it's at the beginning, middle, or end. Since the operations depend only on the local node and its neighbor, the complexities stay constant in all scenarios, making the best, average, and worst cases identical with O1 in both time and space. To put this into perspective, let's compare this solution with a naive or brute force approach. In a brute force method, if we were not given direct access to the node, we would need to traverse the linked list to locate it. This traversal would take n time in the worst case, where n is the number of nodes in the linked list. Furthermore, deleting a node in such a setup might involve additional logic, potentially increasing the complexity. In contrast, the optimized solution we are using avoids traversal entirely. By overwriting the current node's value and updating its pointer, we effectively delete the node in O1 time and O1 space. To mathematically verify, the time complexity remains O1, because the operations do not scale with the size of the list. Similarly, the space complexity is O1, since no auxiliary memory is required. This makes the solution both time and space optimal compared to more naive alternatives. When working with linked lists, there are several common mistakes to watch out for. One of them is not handling the deletion of the head node properly. If the node to be deleted is the head, you must update the head pointer to avoid losing access to the entire list. Another frequent error is assuming the node exists without verifying its presence. Attempting to delete a non-existent node can lead to null pointer dereferences, so always validate the node before modifying pointers. Another pitfall is failing to correctly update pointers. If the previous node's next pointer isn't adjusted to skip the target node, it can cause broken or corrupted links. Finally, infinite loops can occur during traversal if loop conditions or pointer updates are not implemented properly. To prevent this, make sure your traversal logic is clear and well tested, ensuring the loop terminates once the list ends. Edge cases can be tricky and are often overlooked. For example, consider scenarios like deleting the only node in a list, attempting to delete from an empty list, or dealing with multiple nodes that share the same value. These cases need to be explicitly handled in your code and thoroughly tested. From an interview perspective, it's important to recognize patterns. Deleting a node often involves pointer adjustments, which is a common theme in linked list problems, such as reversing a list or detecting cycles. Interviewers also tend to focus on edge cases, so be ready to explain how your solution handles situations like removing a node from a single node list or dealing with null inputs. Additionally, optimal solutions are preferred. Try to avoid unnecessary space or time complexity. Lastly, communication is critical. Walk through your thought process step by step, clearly explaining how you manage edge cases and update pointers. This demonstrates both your technical knowledge and problem-solving approach. Linked list problems often overlap in terms of techniques and concepts. For instance, reversing a linked list, as seen in problems like LeetCode number 206, relies heavily on pointer manipulation. Similarly, removing the nth node from the end of the list, such as in LeetCode number 19, commonly employs the two-pointer technique to locate and delete the target node. Detecting cycles in a linked list, as in LeetCode number 141, involves algorithms like Floyd's cycle detection. Another related problem is merging two sorted linked lists, as in LeetCode number 21, which requires careful pointer adjustments to combine two lists efficiently. Beyond specific problems, you can approach deletion tasks differently. For example, a recursive deletion method traverses the list recursively to find and remove a node. This approach simplifies the code but comes with the trade-off of risking stack overflow for large lists. Alternatively, the dummy node technique involves adding a dummy node at the start of the list, which makes handling edge cases, like head node deletions, much simpler, though it slightly increases memory usage. Another useful approach when working with linked lists is the two-pointer technique. This involves using two pointers to efficiently locate the target node or its predecessor. While this method introduces some overhead in managing the two pointers, it can be particularly effective in specific scenarios, such as finding and removing nodes from the end of the list. This technique not only improves efficiency but also provides a structured way to handle more complex variations of linked list problems. Great job! We've completed the problem, and I hope you now have a clear understanding of how to tackle it efficiently. Remember to review linked list fundamentals, as they are crucial for solving similar problems. Thanks for watching, and don't forget to like and subscribe for more content. See you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!